Okay, thank you for the introduction, and we can start with directly with this presentation outline. We will begin with the motivation and objective part. Next, we will dive in the concept development and implementation. Especially, I am focusing on the corrective parameter delta F tip effective. Following that, I will discuss the implementation of a hybrid optimization method, particularly looking at the parameter unification for cyclic plasticity models. And after covering the numerical and technical aspects, I will present the results of the research. So finally, I will conclude with a short summary. So motivation and objectives. To introduce you in the topic, as we all know, a crack can be considered as the sharpest notch. This sharpness makes classical strength calculation not applicable. Therefore, we use methods of elastic plastic fracture mechanics. So one key aspect we need to address is the plasticity-induced crack closure. This phenomenon occurs when plastic deformation around the crack tip influences the crack's progression and potentially reducing the rate at which the crack grows or even causing it to stop or to close. We also use the node release technique in our simulation here. The techniques helps to model and analyze the crack behavior under various loading conditions by numerically releasing nodes in the finite element model. For accurate numerical calculation, we rely on cyclically effective crack tip parameters. And a short overview I saw in the last conferences or in recent years, we can generally see it here in these three parts here. In recent years, we can generally identify these three numerical types of cyclic J integral implementations in elastic plastic fracture mechanics, starting here on the left, based, or I call this old school implementation based on the experimental findings of Dowling and Begley, as interpreted by, or numerically interpreted by Wüttrich and Tanaka. In the middle, we see the path independent definition according to Aturi and others. And increasingly, we are seeing the variant on the right side involving configurational forces or material forces in this work I present today. I have implemented the method on the left and the method using material forces and comparing them with each other and against experimental results. And in this presentation, I'll call one parameter which is based on Dowling and Begley's idea, delta G effective dB. And on the right, the corrective parameter which is based on the material force theory is called delta F tip effective. So concept development and the finite element approximation. I would like to show you some or four important building blocks for implementing the finite element approximation in this work I used, starting with the invariant properties of thermodynamic conservation laws, which are based on certain principles, such, for example, as the momentum equation or conservation of momentum, conservation of energy, or conservation of angular momentum. On the right side, you see the result of the first step. It's the divergence of the Eshelby tensor. And this Eshelby tensor divergence contains these five parts here. First of all, the dissipation part, then the hardening part, temperature part, volume loads part, and the inhomogeneity part. Next image on the left illustrates the association of path integrals and then domain integrals, which are used to derive the weak form of the mathematical equation you see here on the right side. This leads us to the assembly algorithm for nodal values, I use the algorithm defined by Miller and Gross for calculating the actual corrective parameter ftip. So, and we should, or in this work, I define some kind of effective corrective tip parameter. So you need a kind of crack closure algorithm. And this is programmed also in this work to define this delta tip effective. Okay. And the beauty of the method of material forces within the finite element program Abacus is that it can be easily visualized and demonstrated here with a CT spaceman. That was the first step. Actually, I implemented this method. Now, could you click on the play button on the right side? Okay, it's not so good to see, but I hope you can recognize something, and that are some kind of definitions and nodal points of these material forces. Okay. Yes, and one slide perhaps for the part of the research work concerning the determination of material parameters. I will keep it shortly because you can talk about 1 hour only about this method. We see, first of all, first loading and unloading curve to capture the Bauschinger effect, for example. Next, the cyclic softening tests, and very important, the ratcheting effect. Yes, this is only a kind of picture of the oven to say these parameters are temperature dependent, and you have to have different temperatures. Okay, the right side shows you the least square function and the optimization method I used. It's based on the experimental data, of course, and the cyclic plasticity model or the simulation data. Therefore, I applied here a novel hybrid algorithm, which is very fast as a hybrid, because I use two algorithms of optimization in one optimization program. It's the differential evolution algorithm and the simple one, known linear simplex, or the simplex according to Nelda and Med. Today I present only the results with the Chabosh model, which fits pretty well in this whole concept of thermodynamically consistence. You see here the minimization function to solve this problem. And after you arrange this determination of material parameters, you can define it in the software here. Okay, some results perhaps to show you one of these parameter sets, Chabosh model for the material 42 chromo 4. It's quenched and tempered. It's a German, usually German kind of way to define the name of this material. Two sets for 20 degrees Celsius and 180 degrees Celsius. And everybody who uses this Chabosh model sees at once that I used here only 5 Baxter stencils. Okay, and to show you some quality of this parameter set, I chose an strain control test. It's strain amplitude of 1.5%. Simulated data show good agreement with experimental data, and you see the effect of the cyclic softening. And also after a huge or a defined number of cycles, you see also this stabilization process. Now, to give you an idea what the examined specimen looks like, this illustration is provided. On the left, we see the sample's cross-section views, detailing its dimensions and tolerances. Our finite element model, of course, shown on the right, takes advantage of the sample symmetry and to simplify the analysis. And why is such complicated specimens? Why not in CT specimen? Because that's usual on research work which was the aim was to build up some special components of a common rail system component, and usually you have such 90-degree borehole intersections in it. Yes, a graph showing pressure variations. So it's about the boundary conditions in this work. Over time, during auto-frettage and subsequent loading cycles, initially we apply a maximum auto-frettage pressure denoted as PAF, which reaches 8,500 bar. Following this pressure, you see some operation loading conditions with Pmax and Pmin. And at the start, the temperature is held at 20 degrees Celsius, and then it's ramped to the 180 degrees of Celsius, as indicated by the red line. Then around 250 cycles for the residual stress redistribution. So that's very important because before you start with fracture mechanics, you have some kind of initial condition here. And the node release technique, of course, here follows these steps, is employed where the next segment of the crank front opens after 2 loading cycles, or it's a special number you have to verify, allowing us to simulate crack propagation effectively. Okay, some results to the residual stress redistribution and temperature effects. Really a difficult word for me. At one example here, you see it. The red curves show you the initial residual stress introduced by the auto-frettage process, and after operating pressure load about 251 cycles, you lose about 200 megapascal of initial residual stress in this foreground area. And that's important. You can only reach such results with cyclic as elastic plastic models. It's not possible in another way. Okay, effect of the residual stress on crack tip. I would like to highlight this effect of residual compressive stresses on the crack tip parameter as the crack grows. On the left side, we see the results of the crack tip. For example, here, parameter JDB plotted against the crack length. On the right side, the geometry of the specimen is shown with the initial crack length and the black arrow indicating the current how do you say, crack front. When I press the button here, the crack front expands, and on the left side, we see the corresponding crack tip value in relation to the crack length. Here we go. You see this? Of course, it's simulated also in Abacus, but it's better to present it in this way, because the main point is that in the presence of compressive residual stresses, the effective crack tip values are lower despite an increased crack length. This can even lead to crack arrest, as shown in the next slide. Validation. So you see this on this slide. To keep it shortly, by varying the pressure load, different F-tip curves are obtained so that the crack stop is expected when that red threshold curve is undershot. And you see this here. It's at the case 305 megapascal.
Dario, 1 minute.
Yes. Here the results for the lifetime assessment are shown, and we see that JDB shows higher lifetime values than F-tip in the low cycle range here. In high cycle range, the situation reverses. So the GDB showing shorter wavelengths compared to F-tip. Without going in a detailed explanation, this has to do with dissipative components and the hardening contribution of the respective corrective parameter F-tip, which is not included in this definition of JDB. So however, both methods yield respectable results when compared with the experimental red points here. Okay, that was it.
Thank you.